just to go through a variety of complex number questions. And for a lot of them, you need to be able to do things on your calculator, but also to really understand them and to also be able to do them by hand. So, for example, this one, obviously we can just do it on the calculator. We just type it in and then you go to options complex. You've got some basic things here, so I could find the absolute value. So it's poorly worded, that ABS. That is the magnitude, which is written like this. But this symbol here is not the absolute value in real numbers. So the absolute value of -5 is 5. What this means is the magnitude, the length of this line on the Argand diagram. So we can do it on the calculator, and we just go to this menu and then across, and we have this rather awkward button here, but it means √3 plus I, send this to the r cis theta notation, and we just press enter on that. 2 cis 30, so you write the answer down as 2 cis 30. You should have a very clear understanding what that means. The Argand diagram, which has a real axis and an imaginary axis, 2 cis 30 means a length of 2 and an angle of 30. But look, that fits completely with this. That this is √3 plus I, so it's 1 up and √3 across. Why is it 1 up and not I up? And that's because the imaginary axis takes care of the I. So this is I, but this distance is 1. So what is the length of this line here? Well, Pythagoras tells us √3 squared plus 1 squared square rooted. It's 2. So we could have done this by hand, by Pythagoras to get the length and inverse tan of 1 over √3 to get the angle. By the way, while we're here, this is called polar form, and you can immediately just write that in Euler form by writing down exactly the same thing, but this angle here can't be in degrees, so I'll have to convert the degrees to radians, pi by 6. And so these things are the same: Euler, polar, Cartesian. This one here, now don't let your brain switch off just because it's complex numbers. You think, oh, this must be incredibly hard. We're not going to be able to just type this into the calculator. This is simultaneous equations. How do you do simultaneous equations? You take the easier equation and substitute it into the harder one. In this case, the easier one is here. Z is equal to 2IW. Now I can substitute that into here. So Z was 2IW times W equals -√3 plus I. That I can just multiply out. So it doesn't make any difference that this is complex numbers. It doesn't make any difference at all. We're just doing normal algebra. And so that is, and now this is the moment. This is the APS course. And so, yes, we've got a little bit of algebra and arithmetic, and we just do that, and now we can just type that in. So I would go to the calculator now and type in the square root of this number here. Type it in as I see it. There we are, and then just run that. And it will tell us the answer. And one nice thing the calculator does is it splits it into the real bit and the imaginary bit. So I could have written that as, I factorized the half out. So I could have written it as a half times √3 plus I. And that's a perfectly sensible way to do it, but it's not split fully into real and imaginary. So in fact, the calculator is doing well here. That's nice. A real number plus an imaginary number. That's what a complex number is. Okay. So quadratics, again, don't switch your mind off just because it's complex numbers. You know about quadratics. Quadratics typically look like this. You have factors, and therefore you get roots. These roots are called zeros or solutions or roots. So this is the same thing. we're just going backwards. Given this, can you find the quadratic it came from? Well, I would turn this 3 and 4 into factors and then multiply the brackets out. Let's just do the same thing. So I'm going to start with a root that is 1 plus 2i. Now you should know straight away that there is another one that always for quadratic is the complex conjugate. So there's my two roots. That means the factors must have been this. There's one factor. There's the other factor. And to get back to the original quadratic, I've got to multiply those together. I'll have to do a little bit by hand, a little bit on the calculator. So I've got the x squared. Clearly that's easy. I've got that. Now you could type that into a calculator. Just type those two. No, hold it. One of those should be plus. I could type that into the calculator and just work out what it is. It turns out to be 5. And then probably the best way of doing this is you say x. What have I got? Well, I've got this negative 1 plus 2i times x. Negative 1 plus 2i. Notice the way I've handled the bracket there. And I've also got this negative 1 plus 2i. And then either type that into the calculator or realize it's in fact quite easy. They cancel. That's a minus 2. And so I've got an answer of x squared minus 2x plus 5. And that's equal to 0. That's where these roots must have come from. So roots go to factors, which go to equation. We're so used to going the other direction. Okay, draw an Argand diagram. So not going to draw it accurately. You'll never be asked to draw an accurate Argand diagram. 4 across 1 up, that's Z. 2 across 2 up, that's W. What is Z plus W? Now we could work that out. It's clearly 6 plus 3i, sort of up there somewhere. But we can also do it geometrically. There's W, there's Z. If I make this into a parallelogram, make that a tiny bit more accurate there, something like that. Make it into a parallelogram. That there is W plus Z. And that should look familiar to you. You should be thinking, that's the same as vectors. So there is a geometric interpretation of addition in complex numbers. This one here is just algebra. No problem. I'm just going to use a mixture of calculator and non-calculator. So this here is just calculator. I'm just simply going to type it in. So I haven't just typed the whole equation in. I've just typed that in. I'm going to work that as, so I've got to take it off the screen to press execute and then put it back. There we go. That is what the left-hand side, 5/13 minus 5/13. So this question is now 5/13 minus 5/13 I. That's equal to 10 over. Now there's a really nice trick that you'll see in maths all the time. We've just seen it in differential equations. How do I tidy this equation up? I want to see W equals. Clearly the W is going to multiply up to that side. I'm going to leave the 10 alone. And the whole of that other side, I'm simply going to put it here. It's like a form of cross multiply. The W has gone up. That has gone up. And at the same time, what was there has gone down. They've kind of swapped places. Now, what would you do? Type it into the calculator. So we're doing this mixture of, look at the question again, and saying to yourself, you cannot just type in that to the calculator. The calculator can't solve equations that are complex. However, it can do calculations for you. So I did a little bit, broke it up and said, well, that bit can be done by the calculator. Then I do a little bit of algebra myself. Then I use the calculator again. Lovely hybrid approach. Here we go. So we've got to find x and y in this equation here. And again, we're not typing that into the calculator. We've got to do a little bit of work first. Let's just multiply it out. So I've just multiplied it out. What are you going to do next? Can you tell yourself the answer to that? And that is to put all the real things together and all of the imaginary things together. I'm going to leave the right-hand side. And I'm going to put all the real things here. Clearly 4x is real. And this here, minus 7 yi squared. I squared is minus 1, so that's plus 7y. That's real. What have I got on the i's? I've got the 4yi and the minus 7x. That's an x. And this is so important. You've separated into real and imaginary. Real and imaginary. And therefore, the real bit of this must be the real bit of that. 4x plus 7y is equal to 3. And the imaginary bit, 4y minus 7x, is equal to 2. Simultaneous equations you solve in the normal way. Next one. Okay, so now this time it says let z equals a plus ib. That's just telling you the way it wants the answer written. I could replace z equals a plus ib in there, but can you just do this question? This is the same question as 5x equals 3. How would you do that? You divide by 5. So, you know, try and get this mentality of I'm going to do a bit of working myself, then I'm going to type it in. So this is a little bit of a red herring. You've got to be a little bit careful. They're just saying find z. Last one. Again, this is very similar to one or two that we've already done. Can you do it now? What you should be saying to yourself, I'm going to do a bit of algebra. I'm going to use the calculator a bit. Whatever's appropriate. We can't just type that in. So let's use a bit of algebra. Clearly multiply the brackets out. Zi plus I equals 3z minus 2. We're trying to find z, so I'm going to get all the z's onto one side. And the i's on the other. Factorize and divide. And then type that into the calculator. So there's a little bit of calculator work. I don't have to divide complex numbers by hand. Okay,